Okay, we did cover a bit of a set theory in the first class, but now we will do some more advanced stuff. So as I said, A means A is a member of the set A, right? And I also explained that there are two ways to describe a set. One is to explicitly list all the elements, right? Another one would be to say what you're collecting. Let's say X is what we're collecting, but X has to equals to 2n minus 1, or some n. Now, do you remember what this meant? What is this symbol? Set of all natural numbers. N is for natural numbers. These are 1, 2, 3, 4, 5. So if this is set of all natural numbers, what does this set collect? Natural number times 2 minus 1.
What do you call the odd?
Yeah, all the odd numbers, right? Great. It's a bit noisy here. I'm trying to record. All right, so that's what it is now. So this was what we covered briefly in the first class. Now let me talk about unions and intersections. So A union B is described like this. This is a collection of X such that X is in A or X is in B. That's what a union is. So for example, if we have A and B as these things, then what's A union B? Well, it's 1, 2, 3, 5. Because these belong to A, but B has all the odd numbers, right? So this would be like same thing as 2 added onto all the odd numbers for this specific example, right? On the other hand, if you have A intersect B, okay, guess what I should write here? A intersect B. This would be X in A and X in B. So you're collecting members that belong to both. You're collecting members of sets that belong to both. And you get, in our case, when A and B are defined like that, A intersect B would be, okay, let me see if you can get it. Let me see if you can get it. What's A intersection B?
Is it 1, 2, 3, 5?
1, 2, 3, 5 intersect with all the odd numbers, so what's the intersection?
And 1, 3, 9.
1, 3, 5. Right? Only 1, 3, and 5 belong to both. Okay, and then there's some others like A minus B. This symbol, some people write it like this. Some people write A minus B. So in the literature, you might see either one. I'll use this for this class. So what this means is you're collecting members in A, but X should not be the member of B. So you should write down and. X is in A and X is not in B. Now in our case, what would A minus B look like for these two sets? You have these things, but which one of these do not belong to here?
2.
2, that's the only thing, right? So in this case, it will be just 2.
Wait, why would it be 2?
Because
Just because it's even?
if you write down what B is like 1, 3, 5, 7, 9, all that, right? So if you look at 1 is in here, but this is also in 1, so that shouldn't be included in A minus B. 2 is here, but 2 is not there, so 2 survives. 3 is here and there, so that should be deleted. 5 should also be deleted. So the only thing that survives, if you take out the ones that belong to X, then 2 is the only thing that remains.
Okay.
Right? Now, sometimes there's a U called universal set, and this is not a gigantic set, but it's some set given by the context. So if you're just working in the domain of integers, universal set could mean the set of all integers. If you're working in the set of real numbers, then the universal set could be all real numbers. It really depends, okay? But let's suppose that you're working with some sets, and these sets are subsets of some big set that you're always functioning under, okay? So in such a case, you can talk about the complement of a set, and again, there are two different notations. Actually, there are several notations for this. Some would use tilde over it, but I guess these are the most common ones. So if you see a C for complement or bar, these are sets where you collect things that are in the universal set that's not in B. Okay. So if you adopt this, then you can say that A minus B is same thing as A intercept B complement. Let's use bar, because that's what the textbook uses. Okay. So these are the same. It's not so hard to convince yourself that those two are the same, but by thinking of examples. But perhaps when it comes to showing the equality between two different notations of sets, a nice way to do things would be to use something called a Venn diagram. So there's something called a Venn diagram. Where you think of a universal set, and let's say here's set A, here's set B. The most generic configuration of two sets because it contains all possible things. So if you had some elements here, some elements here, some elements here, some elements here, suppose you had some elements here like that, then these are elements that do not belong to any one of A or B. These are elements that belong to A but not B. These are elements that belong to both A and B. And these are elements that belong to B but not A. Yeah. So this Venn diagram captures all possible ways that a member could be in, right? So, for example, this would be a bad Venn diagram to talk about general identities. If you say A and B, this is not a good Venn diagram because this does not have any elements that's in B but not in A, right? This one, every element in B belongs to A, so that's not a good Venn diagram. Yeah. So if you have a generic Venn diagram written shown like this, and by the way, of course you can draw this Venn diagram to say that this is an example where B is a subset of A, okay? But when you're trying to prove that two things are equal, you really want to have a generic Venn diagram to show that two things are equal, okay? So, let me just, all right, so let me do this again. So my goal is to draw the Venn diagram for this one and show that they are equal. But first, in this generic Venn diagram, what are the elements that are in A but not in B? Can you shade it? Oh, you can shade it, and they're really right here. Right? These are the elements that are in A but not in B. Okay? But then over here, the elements that are not in B are here. So these are B complements, a complement of B. These are the things that are not in B. On the other hand, you have things that are in A. My red is not working well, but you see my point, right? So these are the things in A. Now, what is the intersection between things in A and things that are not in B? The one that's overlapping is exactly this much, right? So this much right here would be A intersect B complement. As you can see, they have exactly the same shaded part, right? So you can show that they're equal. other equalities. So you have A union B complement equals to A complement intersect B complement. And then A intersect B, overall everything complement. I don't need this parenthesis. That's equal to A complement union B complement. Now this has similarities with the other identity that we talked about in logic. If you have P and Q and you have a not operator, that's the same thing as not P or not Q operator, right? You remember doing this the other day, right? Now this has direct counterpart with this guy, right? That's because remember, what is this one? This is and, right? And I know that A and B is what's being collected in this intersection. So because the logic satisfies this, that's why you have these two sets describing the same thing. Okay? And because of that, these two rules carry the same name as what we call this one. Do you remember what this was called? Some Italian guys. De Morgan. Okay, then there's a distributed property. Which is that if you have A union B intersect C, that's equal to A union B intersect A union C. And then you can also switch this around. You can have an intersect and then union. The same thing as A intersect B union A intersect C. Let's see why this one is true. To show that using a Venn diagram, you need to have a set of three things, A, B, C in generic form. And the way you can draw three sets would be you put A, B, and C. Now, for every element inside U, they can either belong to A, not belong to A, belong to B, not belong to B, belong to C, or not belong to C. So there are two possibilities for each of A and B and C. So there are a total of 8 possible cases. A member could be something like, could be a member of A but not B or not C, and you can really think of it that it's like true or false. You can think of the following statement: A belongs to X belongs to A. Is that true or false? Does X belong to B? Evaluate to true or false. What about X belong to C? Is that true or false? Okay, so if you think about that, the total possibilities are 8 because it's 2 times 2 times 2. And in fact, this one does have 8 different regions. You have 1, 2, 3, 4, 5, 6, 7, 8, right? So that represents all the possibilities. That's why that picture is a generic configuration. Now, it's really tricky to do the next one. So the question is, like, can you put a fourth one to get 16 possible domains. Like, how would you put the D to make it generic? I don't know, you try. It's not that easy, okay? Okay, but anyways, at least for the three, this is good. Now let's see how A union B intersects C works. So B intersects C is here, right? And then if you union with A, this is what you get. Okay, that's A union B intersects C. Why is it same as A union B and A union C's intersection? Well, to draw the second one, you get A union C, now A union B is this one, and A union C is this one. Okay, and if you take the intersection between the blue shaded area and the black shaded area, then you can see that the intersection is right here, which is exactly the same place. Okay? That's why this is true. Okay, well, if you do not like showing and convincing yourself these things are the same, another approach would be to use truth tables too. You can also use truth table to show identities of sets. And the way you do it is you can do A, B, C. And let's say I want A union B intersects C. So that's like you want to do B intersects C first and then A union B intersects C. And you again use truth tables to represent the true or false of the following statement. X is in A, X is in B, X is in C. So if you have TTT, that means there is this member X that belongs to all of them, okay? You can also have TTF, could also be TF, and then you write T and F. It can also be F and T, write that twice, and write TF. It could also be FF, write that twice, and you can put TF. And then B intersects C is, remember, this intersection is really the AND operator, right? It's a collection of things that belong to both B and C. So only when it's TT for both of them is true, in which case you have here and here, and all the other cases it's false, right? So you have true and then false everywhere. And now when it comes to union is OR. The definition of A union another set is you have the word OR in there, right? So that's true. That evaluates the true whenever one of them is true, right? So since we're taking the OR between these two, if you see only when you see FF, that's going to be false. So FF here, that's going to be false. Okay, these three cases will be false. Okay, FF. But all the other cases, you have at least one of the truths, true T's. So you get true over here and F for the other guys, okay? And then you do the same thing for the A. What is this one? Let me erase here. Now I should really be writing these columns on the right side, but because I'll be outside the camera, I'll just continue over here. But if you're taking notes, please write these columns on the right side, okay? So what we want to do is we want to calculate this one, A union B, A union C, and then intersection. So A union B, A union C, and then A union B intersect A union C. Okay, so unions are true whenever at least one of them are true, so it's false only when both are false. So here and here, these are the only cases when this first one evaluates to false, right? So it's false here, but all the other cases is true. Okay. And then for A union C, it's these two, and you get false, false here, and false, false here. So these are the two cases you get false. All the other cases you have true. And because we have intersections, you only get true if both are true. If any one of these are false, is false. So these three is false, and all of these are true. And now you compare this one with this, you get the same exact truth tables, and that's how you can prove that these two things are the same. Okay? So on an exam, you might be given questions like, show that these two are the same sets. How can you show it? Well, one way is to show by Venn diagram, or you can make this gigantic table to show that they have the same members. Now, think about a case where your proposition P has a free variable. So here's an example. X is odd. When you have such a case, then the truth value of this depends on which x you choose, right? So you have P of 2. Is P of 2 true or false? Well, just like how you evaluate a function, you plug in 2, and you have the statement 2 is odd. Is that true or false? Oh, false. How about P of 7? 7 is indeed odd, so this is true, right? So you can have a proposition that depends on a free variable, or you might have like x and y. You could have a statement that has x and y, and depending on the value of x and y, it could evaluate to true or false. Now, in such a case, you can define capital P as all the x's that make px is true. Okay? Then, so now you can have something called quantifiers. So you can have all x px. So this means for all x, px is true. That's what it means. And an example of such would be for all x in n, right? X is positive. So that will be a true statement, right? Because this is set of all positive integers, 1, 2, 3, 4, 5. So that's a true statement. E.g. On the other hand, you could have this is exists, okay? So for some x, that's what this means. Or there exists some x such that px. So an example of such is for there's some integers x is divisible only by 1 or x. What's such an example of a number? So for example, 6 is not that sum. 6 is divisible by, so we for convenience, the notation for divisible is like this. So this means 2 divides 6, okay? So 6 is divisible by 1, divisible by 2, 3, and itself. But any number is divisible by 1 in itself, right? So can you think of a number which is divisible only by 1 in itself?
7.
1 is one example. 7 is another example, right? So 7 is an example where 1 does divide 7 and 7 divides 7. Okay? Now, if you add in another condition that x is not 1 and x is not 1, then this is the definition of what's known as a prime number. Okay? Yeah. So this statement is saying that there exist prime numbers inside n. Okay. Now, here's an important observation. If for all x, px implies qx, okay, then p is a subset of q. Okay, so this is let's call this a theorem. Okay, and proof. Well, what does that mean? Because px implies qx, we learned last time that this is the same thing as not p, x, or q. We learned that these two are the same, right? So in terms of the set, the set theoretical equivalence of this one, the truth set for this one would be not p or q. No, sorry, union, not p union q. Does that make sense? If you want the truth, if p is the truth set for px and q is the truth set for qx, okay. So I'm saying p is all the x's that make px equal to true, and q is equal to all the x that makes qx equals to true. Then the set that makes px implies qx true, this is the same thing as the set that's not px or qx. These two are the same because or qx. Because we proved the equivalence of this last time, right? And then This is exactly the union of sorry, this should be true equals to true. But this is P complement union Q, right? Oh, I forgot. This is the notation for logic. This should be really this. Okay. So by this, you can see that the truth set for this is not P union Q, right? So that's what we have. And let's make a truth table for this one as well. T, T, TF, FT, FF. Then, again, the only time that this is going to evaluate to false is when you have here. Right? So these will be okay, but this is false. Okay? Is this fine? No?
Yeah.
Okay. And then to say that for all x, this is true, means that these do not exist. If you have any element that belongs to P but not in F, then you have a case when this proposition is false. Okay? Is that okay? Yeah, see, what are we trying to prove? We're saying that for all x this is true, which means this is everything, okay? Which means this shouldn't exist, this case shouldn't exist. So what does that mean in terms of Venn diagram? It's exactly this portion. This is the portion where it belongs to P but does not belong to Q, right? So that's gone. If that's gone, what does that mean? Everything that's in P belongs to Q, right? Yeah. So if you remove this, that's same as Q containing P. That's what it means, right? Now, let me try to make sense of this theorem in a different way. So I tried to explain that this proposition, if P then Q, is in practice there are two different kinds of if then statements, right? There's like if then or else kind of statement. It's like if you get 100 on the math test, I'll buy you a bicycle. That if then really also says or else if you don't get 100, I'm not going to buy you a bicycle. That's like tacitly in there, right? But there are other cases like in order to get admitted to SUNY Maritime College, you need a 1500 SAT. Is that right? I don't know. But let's say that's true. Yeah, 1500 SAT. And then, but even if that's true, does that mean everyone in this college has 1500 or more in SAT? No, that's not true. Some people might be admitted because they're good in sports, right? Some people may be admitted because they did something exemplary or something else, right? So if X is the student, okay, and we can say something like this. PX is like the student X has 1500 or more SAT score, okay? Yeah. And then QX is student X has been admitted. Not that they came here, but we give them acceptance, okay? So student X has been accepted to the college, right? So now you take U to be the universal set, which means everybody who applied to SUNY Maritime College, okay? Among them, PX, the truth set for PX would be everybody who got 1500 or more in SAT, okay? And QX would be everyone that we gave acceptance letter to, right? Now, what's the inclusion? Is P included in Q or Q included in P? Of course, P is included in Q, right? P is this small group of people who got 1,500 or more in SAT. Does that make sense? So if you have P implies Q, then the truth set for P will be a subset for Q, for this to be true. That's what this is trying to say. Does that make sense? Okay.